Welcome, geologists, earth science enthusiasts, and fellow explorers to the channel where we bridge the gap between complex earth systems and modern analytic techniques. Today, we are tackling two massive concepts that define modern geological exploration and deep time understanding: geostatistics and the profound, beautiful constraint imposed by chaos. We rely on sophisticated tools like Kriging to create precise models, but what happens when the very planet we study turns out to be inherently unpredictable? The geologist's dilemma: modeling uncertainty. As geologists, we face an immense challenge every day. We are tasked with describing complex geological phenomena that stretch across vast geographical areas, often involving subtle and interconnected relationships beneath the surface. Yet, we only ever have measurements involving a tiny fraction of the entire area or volume of interest. We are forced to create models, whether for an oil reservoir or a mineral deposit, based on incomplete knowledge. This means that the results we produce are necessarily uncertain. Interestingly, this uncertainty is not an intrinsic property of the Earth itself. It is the direct result of our limited ability to observe and measure the system fully. Geostatistics emerged precisely to address this issue, becoming firmly established in the 1960s thanks to the pioneering work of French engineer Georges Materon. The main objective of geostatistics is the characterization of spatial systems that are incompletely known. A key difference that separates geostatistics from classical statistics is that it explicitly uses the geographic location of every measurement. If your measurements lack spatial correlation, meaning a sample taken here tells you nothing about a sample taken a few feet away, then applying geostatistics is pointless. When we look at results graphically, perhaps as fishnet plots or maps, we can instantly see the need for predicting attributes across areas far wider than our tiny data points cover. This differs sharply from time series analysis, where users often focus on extrapolating to make forecasts. Geostatistics excels at interpolating, providing robust estimates within the sample boundaries. Kriging, the optimal spatial estimator. Before we jump into advanced spatial modeling, we briefly touch upon the basic language of statistics. A population is the complete system of interest, while a sample is the limited collection of measurements you actually take. In geology, we often call a collection of drill cores a sample, but in statistics, the term refers to the entire collection of measurements taken to represent the population, with each core value being an individual observation. It's a classic case of geological terminology causing unnecessary confusion for mathematicians. A key foundation of geostatistics lies in the concept of the random variable, which characterizes a population or conveys the unknown value an attribute might take at any location. To make sense of our data, initially we use tools like histograms or cumulative frequency plots like QQ plots to organize and visualize the distribution of our attribute values, such as the depth to an unconformity. Organizing this raw data is a critical first step toward understanding the population we are trying to characterize. The heart of classical geostatistical modeling lies in Kriging, which is defined as a form of generalized linear regression. The goal of Kriging is to produce the optimal spatial estimator in a minimum mean square error sense. Kriging is revolutionary because it uniquely accounts for the statistical dependence or spatial correlation among neighboring data points when calculating an estimate. We have several flavors of Kriging depending on what we assume about the mean value across our study area. Simple Kriging requires knowing the population mean, which is often an impossible assumption in real-world geology. Ordinary Kriging A more practical and commonly used method improves on this by allowing the local mean to be constant but unknown. Its brilliant trick is forcing the estimation weights to sum to 1, ensuring the estimate remains unbiased. For attributes that display a clear systematic variation, such as water depth near a shore or temperature across a tectonic plate, we turn to Universal Kriging, also known as Kriging with trend. Universal Kriging removes the assumption of a constant mean altogether, accounting for complex spatial trends. However, as the mathematical complexity of the model increases, unfortunately, so does the inevitable uncertainty in the resulting maps. The Semivariogram, decoding spatial connection. All Kriging methods hinge entirely on accurately modeling the spatial correlation of the data through the Semivariogram. The Semivariogram visually charts how quickly your attribute values become dissimilar as the distance or lag between them increases. This structural analysis is absolutely critical because Kriging uses the Semivariogram model to determine the optimal weights assigned to each neighboring data point during estimation. Modeling the Semivariogram involves fitting permissible mathematical models such as the Spherical, Exponential, or Gaussian models to the experimental data points. Only permissible models guarantee a unique solution and non-negative estimation variance, ensuring our math doesn't break down later. Through careful semivariogram analysis, we can detect essential characteristics such as anisotropy, whether the correlation structure differs along various directions, or the nugget effect, which represents small-scale variability or measurement error at zero distance. A key practical step in geostatistical workflow involves checking for trend. If a trend exists, the experimental semivariogram can become an artifact, increasing monotonically and reaching values far beyond the actual sample variance. To manage these complex steps practically, modern geologists use powerful software packages like SGS, the Stanford Geostatistical Modeling Software, a user-friendly tool that allows us to input data, define grids, model the semivariogram, and run complex estimation algorithms, saving the resulting estimated maps and error surfaces as electronic files. The Kriging Estimate ERROR, the smoothing effect. Despite Kriging's mathematical elegance and optimality in minimizing the mean square estimation error, it suffers from a major weakness, the smoothing effect. This effect becomes painfully obvious when sampling is sparse. If the average sampling interval is large compared to the spatial correlation range, maps produced by Kriging lose realistic detail. In short, Kriging tends to oversmooth reality, underestimating high values and overestimating low values, creating a map that is too blurry to show true geological texture. This smoothing is a critical reason why estimation methods like Kriging often fall short when we need a realistic representation of the full geological variability. This weak side of Kriging motivates the use of stochastic simulation methods such as Sequential Gaussian Simulation, SGS. Stochastic simulation fundamentally differs because instead of producing a single optimal estimate, it generates multiple equiprobable realizations of the attribute across the domain. Because these realizations are designed to reproduce the input data's histogram and semivariogram model accurately, they preserve the actual spatial variability and texture that Kriging smooths away, providing a crucial tool for modeling uncertainty. This transition from estimation to simulation is one of the biggest leaps in modern geological modeling. Chaos theory. determinism without predictability. Now let's pivot from our deterministic models of the Earth to the fundamental physics of the universe and why predictability is short-lived. Chaos theory is an interdisciplinary field focusing on deterministic dynamical systems that are highly sensitive to initial conditions. This sensitivity is popularly known as the butterfly effect, where a minuscule change in one part of the system, like a butterfly flapping its wings, can result in vastly different outcomes later on. The critical thing to understand is that chaotic is not the same as random. A truly random process is totally unpredictable. Knowing what happened previously gives you absolutely no clue what will happen next, like predicting when the next raindrop will hit your nose. Chaos, however, falls between the two extremes of total predictability and total unpredictability. Chaotic systems are governed by deterministic equations, meaning their past and present uniquely determine their future. But because their trajectories diverge exponentially fast from even slightly different starting points, long-term prediction becomes physically impossible for human intellect. As the great Henri Poincaré stated, a small error in the initial conditions will produce an enormous error in the final phenomena. We can model the chaotic system like the complex double pendulum or the Earth's atmosphere with known physical laws, but the outcome is so hypersensitive to the initial state that we effectively lose the capacity to know exactly how it will develop in the future. The unpredictable clockwork of the solar system. This concept of deterministic chaos is absolutely fundamental to understanding the stability of our solar system and, consequently, the Milankovitch cycles that pace Earth's climate. Astronomical solutions, or AS, are calculations of planetary, orbital, and rotational parameters based entirely on the known dynamics and physics of the solar system. This work, which began in earnest with Milutin Milankovitch in the early 20th century, revolutionized our understanding of paleoclimatology and geologic dating by linking climate fluctuations to long-term changes in Earth's orbit, eccentricity, obliquity, and precession. The application of modern AS has allowed for the development of the astronomical time scale, ATS, which provides highly accurate geological dates with incredibly small error margins over the past tens of millions of years. However, the solar system is itself a large-scale chaotic system, a fact confirmed by independent numerical studies. The inner solar system, including Earth's orbit, exhibits a chaotic behavior characterized by a Lyapunov time of only about 5 million years. This Lyapunov time represents the exponential divergence rate of nearby trajectories, and it imposes a fundamental physical limit on predictability. We have found that modern orbital solutions, even highly accurate and geologically constrained versions like ZB18A and ZB20X, begin to diverge quickly beyond approximately 50 million years in the past. Beyond this divergence time, the probability that any single computed AS represents the actual unique history of the solar system becomes near zero. This chaos compromises the reliability of even seemingly stable cycles over deep time. For instance, the famed 405 kilo-year eccentricity cycle, related to the stability of Jupiter and Venus, and such an astronomical metronome for deep time applications because it appeared practically stable. However, new research shows that even this supposedly stable cycle can become unstable over hundreds of millions of years due to secular resonances. The reality is that the current evidence does not support the existence of universally stable astronomical metronomes for deep time. In essence, chaos theory imposes a predictability limit. The quest for a single deterministic solution that describes the solar system's evolution for all time often referred to as Laplace's demon, must be regarded as unrealistic. We cannot overcome this physical limitation, even with ever faster computer algorithms and increasing precision. Mabim navigating the chaotic earth, so we return to the geologist on the ground, you. You must use precise mathematical tools like Kriging and geostatistical modeling, which rely on the deterministic behavior of spatially correlated data. Yet, the history of Earth's climate and the long-term tectonic forces we try to model are fundamentally constrained by chaotic, non-linear dynamics. The task is not about finding perfect prediction, but about quantifying uncertainty and constraining the vast number of possible scenarios. That's why we move beyond just the single best Kriging estimate, which smooths out reality, toward generating stochastic simulations that capture the necessary complexity and chaos. In the face of a chaotic world, the best we can do is model large ensembles of possibilities, discarding those that don't match the geological record we see today. If you are interested in these subjects, please subscribe, hit the like button, leave a comment, and share this channel with your friends. Until next time.
Welcome to my channel, where you'll find over 2,000 videos on geology, geochemistry, AI, and many other subjects. If you like what you see, help us grow by subscribing, liking, and sharing this channel.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.